So we know that atoms have existed since the very beginning of time, but the ideas regarding the existence of atoms didn't really come about until the early 400 BC, when Leucippus and Democritus proposed the idea that atoms do exist. So these Greek philosophers basically proposed that matter is composed of indestructible particles. They call them atomos. This is Greek word for uncuttable. So they said that matter can't be sliced forever. That you can't cut it indefinitely. That at some point in time you're gonna reach the limit, the smallest part of matter. They also proposed that there are many different kinds of atoms, each different in shape and size, and that they move randomly through empty space. And so these early ideas regarding the existence of atoms were ahead of its time. There were a lot of detractors, right? There were a lot of other Greek philosophers who opposed these early ideas regarding the existence of atoms. Just to name a few, there's Plato and Aristotle. They were against these ideas regarding atoms. So they didn't embrace these atomic ideas. Instead, they believed that matter had no smallest parts, that you can cut it forever and you'll never reach that smallest part of matter, and that different substances were made of earth, fire, air, and water, or a combination of these four elements. And because Plato and Aristotle were more influential at that time, the other people, basically trashed the early atomic ideas. And for millenniums, for thousands of years, they believed that everything was made of earth, fire, air, and water, or a combination of these four. So let's fast forward many centuries later, all the way to the development of the scientific method. So the scientific approach or scientific method basically became the established way to learn about science, to learn about the physical world. You come up with an idea, you test that idea via experiments, and then prove that idea using solid experimental evidence. And so in the early 1800s, John Dalton offered convincing evidence that supported the early atomic ideas first proposed by Democritus and Leucippus. So basically what he did was he summarized other people's work regarding the existence of atoms and published it in his atomic theory. And then other scientists did some experiments that basically supported this atomic theory. And one of these scientists was Albert Einstein himself. And he tried to prove the existence of molecules and atoms via his work regarding Brownian motion. So first, let's take a look at the law of conservation of mass. So it was Antoine Lavoisier, a French chemist, who first formulated the law of conservation of mass. He basically stated that in a chemical reaction, matter is neither created nor destroyed. So in other words, mass is conserved. So in a chemical reaction, the total mass before the reaction should equal the total mass after the chemical reaction. And so this law is basically consistent with the idea that matter is composed of small indestructible particles. Let's consider this chemical reaction equation here, where you're reacting solid sodium with chlorine gas, and this forms table salt, sodium chloride. So if we started out with 7.7 grams of sodium, and you reacted this with 11.9 grams of chlorine gas, then you would get a total of 19.6 grams of sodium chloride, assuming that this chemical reaction goes 100%. So this leads us to John Dalton and his atomic theory. And his atomic theory can be summarized into four postulates. Okay, and so we're going to list all 4 postulates here, but just FYI that some of these postulates are considered partially invalid today, and we're going to explain why. So the first postulate states that each element is composed of indestructible atoms. Okay, so this first one right here is partially invalid because we know today that atoms can be destroyed, right? They're not exactly indestructible. You can split an atom, and that's what atomic bomb is. The second postulate states that all atoms of a given element have the same mass and other properties that distinguish them from the atoms of other elements. So this is also partially invalid because we know that not all atoms of the same element is the same. Okay, they're not the same exactly because of the presence of what they call isotopes, and we're going to talk about isotopes later on. And the third postulate states that atoms combine in simple whole number ratios to form compounds. And the last one, atoms of one element cannot change into atoms of another element. Okay, otherwise that would be alchemy, and alchemy doesn't exist. In a chemical reaction, atoms only change the way that they are bound together with other atoms. So that basically summarizes Dalton's atomic theory. So when Dalton published his work regarding the atomic theory, a lot of the scientists, like physicists and chemists, jumped into the field because they want to learn more about these atoms, what they're made of, and what they look like. Okay, and so we know today that atoms are composed of subatomic particles, and the first one that was discovered is the electron. So J.J. Thomson was a research professor from Cambridge University, and he did extensive work regarding cathode ray tubes. And he's actually the guy who discovered the electron. So when you go to a gas station, you see these neon lights, right? Neon lamps or neon signs. That's basically what cathode ray tubes are. So when you look here at the bottom right corner, you see this. This is basically the device, the cathode ray tube device that J.J. Thomson came up with. So you have this glass tube right here, which is filled with an inert gas. Okay, so it could be a neon gas, could be argon gas, helium, any of the noble gases or inert gases. And then he capped it with electrodes and hooked it up to a electrical source. And he basically discovered that when you run electrical energy or electricity, a beam of particles traveled from the negative electrode, known as the cathode, to the positive electrode, known as the anode. He also found that these particles, these cathode rays, travel in straight lines. They are independent of the composition of the material used, and that they carry a negative charge because of the fact that these particles traveled from the negative electrode to the positive electrode. Thomson performed several more experiments by measuring the charge to mass ratio of the particles, which he determined as negative 1.76 times 10 to the 8th power coulombs per gram. And that's when Thomson basically discovered the electron, which is a negatively charged particle present in all atoms. And in 1906, Thomson received the Nobel Prize in Physics. He had an idea of what an atom might look like structurally. And so he proposed that the negatively charged electrons were small particles held within a positively charged sphere. And he called this model the plum pudding model. And plum pudding is basically a British dessert. And then J.J. Thomson, again from Cambridge University, he had a student, a PhD student at the time, Ernest Rutherford, and he asked Rutherford to confirm whether this is true, right? So again, he had a hypothesis that of what an atom looks like. And so, like any hypothesis, you got to prove it experimentally and support it with solid evidence. solid physical evidence. And so Rutherford tried to confirm Thomson's model using this or via this experiment called the gold foil experiment. So what exactly is this experiment that Rutherford performed to confirm Thomson's hypothesis or Thomson's plum pudding model? Well, this gold foil experiment, or in this experiment, Rutherford directed positively charged alpha particles at an ultra-thin sheet of gold foil. And the idea behind this experiment is that if the plum pudding is correct, then these alpha particles that were directed through the gold foil will pass through the foil, because these alpha particles are a lot heavier in comparison to electrons. So this is how they designed the gold foil experiment. They had a source of alpha particles that were basically directed at a gold foil, and then this gold foil is surrounded by detectors that can detect alpha particles. So the mass of an alpha particle is similar to the mass of a single atom of helium, and helium is 4 times heavier compared to a hydrogen atom. And a hydrogen atom contains 1 proton and 1 electron, and the mass of an electron is 2,000 times lighter compared to the mass of a proton. So you can imagine an alpha particle shooting at an electron, right? So if the plum pudding model is correct, you're basically saying that this gold foil is composed of a bunch of electrons surrounded by positive charge. And so if the plum pudding model is correct and you shoot an alpha particle at a gold foil, then these alpha particles should be able to just pass through the gold foil. It's like saying, throwing a baseball in the air, right? And the air molecules would not affect the trajectory of that ball. So they shot a bunch of alpha particles at this gold foil, and the result of this experiment took everyone by surprise. Most of the alpha particles passed through with little or no deflection. Some of the alpha particles were deflected at smaller angles, while some at even larger angles. So that suggested that these alpha particles hit something extremely heavy, something massive. It's like that baseball hitting a wall and it bounced right back. So Rutherford concluded that the plum pudding model was incomplete. Something else was missing, something massive. So again, the result of the gold foil experiment was completely unexpected, because the majority of the particles passed through the foil, while some were deflected and others bounced back. And so Rutherford came up with a new model of the atom, and he called it the nuclear model. So this summarizes Rutherford's nuclear model. So he said that most of the atom's mass and all of its positive charge are contained within the nucleus, which is located in the center of the atom. And most of the atom's volume is basically empty space throughout which tiny negatively charged electrons are dispersed. And finally, the number of electrons outside of the nucleus equals the number of protons, which basically makes the atom electrically neutral. And protons are the positively charged subatomic particles. Although Rutherford's model was successful, especially in disproving the plum pudding model, it was still considered incomplete because it couldn't explain why helium is 4 times heavier compared to a hydrogen. A helium atom contains 2 protons, whereas a hydrogen atom contains 1 proton. And so why is it that a helium atom is 4 times heavier compared to a hydrogen? And so something else was missing. And that's basically the neutrons. So about 10 to 15 years later, James Chadwick discovered the neutrons. And the neutrons are the neutral subatomic particles. They don't have any charge, unlike electrons and the protons. Protons are positively charged, electrons are negatively charged, the neutrons are uncharged. And it was James Chadwick who discovered them. And this is Jimmy Neutron from the show. A neutron's mass is similar to a proton's, and so a neutron is technically a lot heavier compared to an electron, similar to a proton. So these are their relative masses. So proton's mass is 1.673 times 10 to the negative 27 kilogram, whereas a neutron has a mass of 1.675 times 10 to the negative 27 kilogram. And so helium is 4 times heavier than hydrogen because it contains 2 protons and 2 neutrons, whereas a hydrogen atom contains only a single proton and an electron, but with no neutron. So this table right here summarizes the relationship between the 3 different subatomic particles in terms of their mass and relative charge. So again, these right here are the actual charge of the subatomic particles, but relatively speaking, we can simplify that into just positive 1 for proton, 0 for neutron, and negative 1 for electron. So in the previous chapter, you learned about elements and how they're different from compounds. Both elements and compounds are types of pure substances. The difference between them is that elements are the simplest building blocks of matter. And the reason why is because you can't break them down further by any physical or chemical means. And there's a lot of different types of elements. So when I show you later, a periodic table basically consists of over 100 different elements. And these elements are different atoms. And so you have over 100 different atoms in the periodic table. You have a hydrogen atom, a helium atom, nitrogen atom, gold atom, silver, so on and so forth. So the question here is, what makes an element different from any other elements in the periodic table? In other words, what makes an element unique? And we can answer this question by looking at the element's number of protons. So every single element in the periodic table will have a unique number of protons. A hydrogen atom contains 1 proton, a helium atom contains 2, and so on and so forth. So there's no 2 elements in the periodic table that have the same number of protons. Elements are defined by their number of protons. So let's take a look at these elements listed here. We have hydrogen, helium, carbon, gold, and silver. When you look at the periodic table, you'll be able to determine the number of protons for any of the elements in the periodic table. Hydrogen, for example, has 1 proton. Helium has 2, carbon has 6, gold 79, and silver 47. And as I mentioned earlier, you won't see 2 elements in the periodic table with the same number of protons. So when I ask you which element has 6 protons, there's only 1 element in the periodic table containing 6 protons, and that's carbon. So how do we determine the number of protons for any of the elements just by looking at the periodic table? The number of protons of any element can be determined by its atomic number. Okay, so for example, hydrogen has a symbol H in the periodic table, and you'll see a symbol H and then a number up top and then a number below or beneath the symbol. The number up top is what they call the atomic number, and the atomic number tells you how many protons there are for that specific element. And so hydrogen has an atomic number of 1, carbon has 6, nitrogen has 7, oxygen has 8. And so by simply looking at an element's atomic number, you'll be able to identify how many protons there are for that specific element. So in this case, hydrogen has 1 proton, carbon has 6, nitrogen has 7, and oxygen has 8. So we can also list the atomic number for the elements shown here. Again, hydrogen would have an atomic number of 1, helium has 2, carbon has 6. Basically, it matches the number of protons. So gold has 79, silver has the atomic number 47. So an element's atomic number can tell us how many protons there are for that specific element. But it can also indicate an atom's number of electrons. And we can easily do that if we're talking about a neutral element or a neutral atom. So what that means is that you have an atom with 0 charge. Okay, so it doesn't have a negative charge or a positive charge. And so in that case, if we have a neutral atom, the number of protons equals the number of electrons. So all the atoms or all the elements in the periodic table are considered neutral. And so the atomic number basically indicates the number of electrons as well. So hydrogen will have 1 electron, carbon has 6 electrons, nitrogen has 7, and oxygen has 8 electrons. And so as you can see, because protons are positively charged and electrons are negatively charged, they cancel each other out. Okay, and that's what makes an atom neutral. So looking at gold has 79 protons, therefore it will have 79 electrons. Silver has 47 protons, and so it will also have 47 electrons. So this is what a periodic table looks like, and there's currently 118 known elements in the periodic table. Make sure you have a copy of this table. You can access this in the course content. You can also look at the back of your book online, or if you have a physical copy, and it's also available in your lab manual. So again, this is the periodic table. Make sure that you know the symbols and names of the first 54 elements in the periodic table. Okay, so from hydrogen all the way to xenon, number 54. Okay, including the elements gold, number 79, platinum, number 78, mercury, number 80, and lead, number 82. So right below the atomic number is the element's symbol. So the example we have here is hydrogen, which is the first element in the periodic table. And the first letter in the element's name matches the element's symbol. Okay? And this is true for elements with a single letter as their symbol. And there's only a few of them in the periodic table. There's carbon, nitrogen, oxygen, there's fluorine, phosphorus, sulfur, and some others. Okay, and they all have symbols that basically match the first letter in their name. Okay, hydrogen capital H, carbon capital C, nitrogen capital N, and oxygen capital O. Most of the elements in the periodic table have symbols consisting of at least 2 letters. And as you can see, the symbol matches the first 2 letters of the element's name. Some elemental symbols don't actually match the name of the elements in the periodic table. And the reason why is because some of the symbols are Latin-based, and some are Greek-based, and others are based off of the place where they were discovered, or it's named after scientists, famous scientists. So the example we have here is SN and AU. So SN is the element tin, AU is the element gold. And you can see that the symbols are based off of their Latin words, like for example, stannum for SN and aurum for AU. Some of the symbols are based off of Greek words like chloros for chlorine. Other symbols are based off of the place where they were discovered from. Like for example, BK is berkelium, which is the element that was discovered in Berkeley National Lab. And then we also have Einsteinium, which is named after Albert Einstein. Other elements that are named after famous scientists are curium and seaborgium. So when you're looking at an element in the periodic table, there are three things that you need to know. The first one is atomic number, the second one is the symbol, and the third one is called the atomic mass. And the atomic mass typically has a symbol called AMU, or atomic mass unit. But before we get into the detail regarding atomic mass, let's first talk about isotopes and how they're different from a normal atom. So isotopes are basically atoms of a given element with different number of neutrons. So in other words, all atoms of a given element can have the same number of protons because they have the same atomic number, but not necessarily have the same number of neutrons. And we'll talk about what makes an element or an atom different, slightly different compared to another atom of that same element. Let's look at carbon, for example. So we know that carbon has the atomic number 6, and therefore it has 6 protons. Now, if this carbon is a neutral carbon atom, then it also has 6 electrons. The majority of carbon atoms actually contain 6 neutrons, but some carbon atoms contain 7, 8, or more neutrons, and those are the isotopes of the element carbon, different isotopes of carbon. So how do we differentiate or tell the difference between the isotopes of a given element? So let's look at hydrogen, for instance. Hydrogen has a total of 3 isotopes. Neon also has 3 isotopes. So when we look at the 3 isotopes of hydrogen, we have hydrogen, the normal hydrogen, deuterium, and tritium. So these are the 3 isotopes of hydrogen. Now, they all have the same atomic number because they're all isotopes of the same element. And so in that case, they have the same number of protons. What makes them different is their number of neutrons. For example, hydrogen on the far left here has no neutron. It has 0 neutron. Deuterium has 1 neutron and tritium has 2 neutrons. Now, when you add these numbers together, what you get is what they call the mass number of that isotope. Okay, so the mass number of the normal hydrogen is 1, mass number of deuterium is 2, mass number of tritium is 3. And it matches the number that's up top right next to the symbol. Okay, and so again, this number is called the mass number. And it tells you, or the mass number is basically the sum of the number of protons and number of neutrons for that given isotope. And so this is the most common notation for isotopes, and it can tell you a lot of things, right? So you have the symbol of the element, and then you have the mass number up top, which is usually a larger number, and the atomic number at the bottom. Okay, so this is slightly different from what you would see in the periodic table, because the elements in the periodic table, those are the average values. Okay, and we'll talk about that in a little bit more detail later on, but we're focused on isotopes. Okay, so this is the most common notation, and it tells you what the mass number is, the atomic number, and just by looking at those numbers, you'll be able to get the number of protons, the number of neutrons, and the number of electrons. Okay, and these are the symbols for these subatomic particles. So protons, the proton is given the symbol P with a positive charge because protons are positively charged subatomic particles. Neutrons are given the symbol N with a 0 charge. Electrons, symbol E with a negative charge. And so again, when you have this notation, in order to get the number of neutrons, all you have to do is subtract the two numbers, right? The mass number and the atomic number. So mass number minus the atomic number gives you the number of neutrons. So now let's look at the three different isotopes of neon. So neon 20, neon 21, and neon 22 are three isotopes of the element neon. As you can see here, the notation here is different from what I just showed you. So this is the second most common notation for writing isotopes of a given element. And so this number right after the name of the element is its mass number, the isotope's mass number. So neon 20 has a mass number of 20, neon 21 has 21 mass number, and so on and so forth. And so the difference between this second common notation versus the first one is that this doesn't tell you what the atomic number is of the element. And so you would have to look at a periodic table and find out what the atomic number is for that specific element. And so when you look at the periodic table, neon has the atomic number 10. So that means that it has a total of 10 protons. So all of these isotopes of neon each has 10 protons. And so how do we determine the number of neutrons for these isotopes? Well, we know that mass number is the sum of the number of protons and number of neutrons. If you know what the number of protons is, then you can just subtract that from the given mass number. And so in this case, for neon 20, subtract 10 from 20, and you get 10 protons for the isotope neon 20. Okay, so you can again set it up algebraically if you want. 20 equals 10 plus x, where x is the number of neutrons. And so you isolate x from the equation and you get 10 neutrons. Okay, and you can do the same thing for neon 21. All you have to do is subtract 10 from the mass number 21 and you get 11 neutrons. And then same thing for neon 22. 22 minus 10 is 12 neutrons. All right, so let's look at another example here. What are the atomic number, mass number, and symbol of the chlorine isotope with 18 neutrons? So chlorine has several isotopes, but how do we determine the symbol, the atomic number, and the mass number of this specific chlorine isotope? So when you look at the periodic table, you can get information from chlorine. So the atomic number of chlorine is 17, and so that means it has 17 protons. The symbol for chlorine is Cl, and in order to determine the mass number, you need the number of protons, and you can get the number of protons from the atomic number. And so it tells you that this isotope has 18 neutrons, right over here. It says chlorine isotope with 18 neutrons. And so in order to get the mass number, we need the number of neutrons and the number of protons. Add them together and you get the mass number. So in that case, we have 35 as the mass number for this specific chlorine isotope. And so 35, how did we get 35? Well, 17 plus 18 gives us 35. And the symbol for chlorine is Cl. So we can write the notation for this specific isotope. It didn't ask in this question, but just for practice, you have chlorine, symbol chlorine, and then the mass number up top on the left hand side, and the atomic number at the bottom. So in this case, we have 35, the mass number up top, and the atomic number at the bottom, 17. Or you can use the second most common notation, which is simpler. You just write down the name of the element or the symbol of the element, followed by a dash, and then the mass number. Okay, so Cl-35. That works too. And here's another example. How many protons, electrons, and neutrons are present in an atom of chromium 52? Okay, so this is a specific isotope of chromium with a mass number of 52. And again, the number at the bottom here, number 24, that's the atomic number. So right off the bat, you know the number of protons of this specific isotope, which is 24. And when you subtract the two numbers, the mass number and the atomic number, it gives you the number of neutrons for that specific isotope. So 52 minus 24 gives you the number of neutrons. So in that case, we have 28 neutrons when you subtract the two numbers. And if we assume that this isotope is neutral, meaning it doesn't have any charge, then the number of electrons is also 24. It matches the number of protons. So we just looked at isotopes, and by definition, isotopes are atoms with different number of neutrons. Now, what if we have atoms with different number of electrons? So these are called ions. Ions are atoms of a given element with a net charge because they have different number of electrons. There are two different types of ions. We have cations and anions. Cations are ions with a net positive charge. Okay, and here are some examples. You have sodium plus, magnesium 2 plus, aluminum 3 plus, lead 4 plus, and manganese 7 plus. So this is basically how you would write the symbol of an ion for a given specific element. And if you remember, an atom has a neutral charge. Okay, typically has a neutral charge. So when you look at all the elements in the periodic table, those are atoms with a neutral charge. And the reason why they have a neutral charge is because they have the same number of protons and electrons. So you know that protons are positively charged, electrons are negatively charged. And so if you have the same number of positive and negatives, then they cancel each other out and you have a zero charge. Now, what if you have one less negative charge? So if you take away one electron from a given atom with a neutral charge, then it becomes positively charged with a positive one charge because you remove one electron. So cations are the result of atoms losing electrons. And so when you look at some examples here, sodium plus means that sodium has lost one electron, magnesium 2 plus has lost 2 electrons, and lead 4 plus has lost 4 electrons. Okay, so overall they would have a net positive charge. Anions, on the other hand, are the opposite of cations. They are negatively charged ions. And here are some examples. We have fluoride ion, chloride, oxide, sulfide, nitride, and phosphide ions. So they all have a net negative charge. So again, a neutral atom would have a zero charge, right? Because the number of protons and number of electrons are the same. But now, what if you added one extra electron to a given neutral atom? Okay, so now because you're adding a negative charge to it, then it becomes negatively charged overall. And so anions are the result of atoms gaining electrons. So for instance, if we look at fluoride ion, oxide, and phosphide, the fluoride ion has a negative one charge, which means that it gained one extra electron. Oxide ion has a negative 2 charge, so it has gained a total of 2 electrons, and the phosphide ion gained a total of 3 electrons. So let's look at some examples here. Determine the number of protons and electrons in each ion. So here we have a combination of positively charged cations and negatively charged anions. So in order to determine the number of protons, all you have to do is find that element in the periodic table so that you can determine what the atomic number is. And so look at the atomic number for nickel. It's number 28. So once you find out what the atomic number is, you'll be able to determine the number of protons for that specific element. And from here, you can determine the number of electrons just by looking at the net charge of that specific ion. So the atomic number of nickel, again, is 28, and so the number of protons is also 28. Now, when you look at the net charge of nickel, it's positive 2. So that tells us that it has lost 2 electrons. So all you have to do is subtract 2 from the number of protons, which gives us 26. Okay? Because originally, before it lost the 2 electrons, the net charge was 0, okay, for a neutral atom. So the number of protons equals the number of electrons. Now, once you remove 2 electrons, it becomes net positive. And now let's look at sulfur. The atomic number of sulfur is 16, and so the number of protons is also 16. And a net negative 2 charge tells us that sulfur has gained 2 extra electrons. And so all you have to do is add 2 to the number of protons, which is 16. And so now we have 18 electrons. So it has 2 electrons more than the number of protons. Bromine in the periodic table is number 35. And so the number of protons is also 35. And because it has a net negative charge, you add 1 electron to the number of protons, which gives us 36. What about for chromium with a positive 3 charge? So chromium in the periodic table is number 24. And so the number of protons will also be 24. And a positive 3 means that you subtracted 3 electrons. And so we would have a total of 21 electrons. And you can do the same thing for iron 3 plus and iron 2 plus. Both iron will have the same atomic number, and so they would have the same number of protons. All right, and the number of electrons would be subtract 3 from 26, and you get 23. And for number of electrons for iron 2 plus, subtract 2, and you get 24. So now let's switch gears and look at the periodic table. So there's a lot of information that you can get from the periodic table, not just the symbol, the atomic number, mass number, or atomic mass. There's a whole lot more. And we're going to dissect the periodic table. But before we do that, let's look at the history of how the periodic table was put together. So the man behind the first version of the periodic table is Mendeleev, Dmitry Mendeleev. So he basically found patterns in the physical and chemical properties of the elements, and so he arranged them based on those patterns. So at that time, around 1800s, there were only about 50 to 60 elements that were known. And so Mendeleev discovered that when these elements are arranged in order of increasing atomic mass, similar properties recurred periodically. For example, when you look at the elements in blue, we have lithium, sodium, potassium. They all have similar properties, similar physical and chemical properties. When you look at the other elements with the same color, we have helium, neon, and argon. They also have similar properties. So then he organized these elements in order of increasing atomic mass in a table and in rows, so that these elements with the same physical and chemical properties fall in the same vertical columns. So when you look at lithium, sodium, and potassium, they all now in the same vertical column. The elements in purple, beryllium, magnesium, and calcium also fall in the same vertical column, and so on and so forth. So shown here is the original version of Mendeleev's periodic table. So he noticed that when he arranged the elements in increasing atomic mass and in columns, he noticed these empty spots here. Okay, and he realized that these empty spots are for elements that haven't been discovered yet. So the beauty of using this table that Mendeleev had created is that you can make predictions. You can predict the physical and chemical properties of those elements that haven't been discovered yet. And so, for example, when you look at this element here labeled Eka in the same column as titanium and silicon, Mendeleev predicted what these what properties, physical and chemical properties, this element would have. So he actually called this element ecasilicon, meaning similar to silicon. And these right here are the physical and chemical properties that he had predicted for ecasilicon. He predicted that the color would be gray, the atomic mass would be 72, density 5.5, and density of the oxide 4.7, and so on and so forth. And then about 20 years later, they discovered that element, ecasilicon, and it turns out it was germanium. Okay, and germanium has many similar properties, physical and chemical properties, that Mendeleev had predicted 20 years ago, or 20 years prior. Now let's look at the modern periodic table, the periodic table that we have today. Henry Moseley discovered that the nuclear charge is just the fancy term for number of protons. The nuclear charge increased by 1 for each element on the periodic table. And he actually suggested that arranging the elements in order of increasing atomic number instead of increasing atomic mass can explain the properties of these elements a lot better and more consistently. So for example, if you look at cobalt and nickel in the periodic table, cobalt comes first because its atomic number is 27 and nickel's atomic number is 28. But cobalt's atomic mass is actually higher than nickel's atomic mass. And so if the periodic table was rearranged in order of increasing atomic mass, then nickel would come first before cobalt. Another example is argon and potassium. So when you look at argon, the atomic number is 18 and potassium has atomic number 19. And potassium has an atomic mass of 39.09, which is higher than argon's lower than argon's 39.95. And so again, if you were to rearrange the elements in terms of increasing atomic mass, then argon would be in potassium's place. Okay, and it doesn't make sense because, as you'll learn later on, potassium is highly reactive, whereas argon is a highly stable element, and so it doesn't make sense for argon to be in potassium's place and vice versa. And so the modern periodic table contains a lot more elements than Mendeleev's original table today because more have been discovered since his time. And the elements are listed in order of increasing atomic number rather than increasing atomic mass. So when you look at the periodic table of the elements, these elements can be classified into 3 categories: metals, nonmetals, and metalloids. And we're going to talk about every single one of these in a little bit more detail. So here's the periodic table, and all the elements that are inside this blue perimeter here are the metals. And the metals have very specific physical and chemical properties that are different from those of the nonmetals and the metalloids. So for example, the metals are good conductors of heat and electricity. They are malleable, which means that they can be hammered into different shapes. They are ductile, which means that they can be drawn into wires like copper wire and so on and so forth. They are shiny, and that's why they're used as jewelry. They tend to lose electrons, and so that means that they tend to gain a positive charge because they're losing electrons, negatively charged electrons. The nonmetals, on the other hand, are the complete opposite of the metals. So all the nonmetals in the periodic table are within the purple perimeter. And again, the nonmetals have very specific physical and chemical properties. There are 17 nonmetals. 5 of them are solids at room temperature, 1 is liquid at room temperature, and 11 are gases at room temperature. They typically are poor conductors of heat and electricity. They are not ductile. They are not malleable. In fact, they are brittle. So if you look at pencil lead, for example, it's made of graphite, and graphite is just a bunch of carbon atoms. And so you can easily break these graphite materials. And they tend to gain electrons, which means that they tend to gain a net negative charge. And the last category we have here are the metalloids. And the metalloids are also known as semi-metals. In terms of properties, physical and chemical properties, the metalloids have mixed properties. Okay, so they have some properties similar to the nonmetals, while some are very similar to the metals. So they're kind of like in between the nonmetals and the metals. Several metalloids are classified as semiconductors, and silicon is one perfect example. So the periodic table can also be categorized in terms of their predictability regarding the element's physical and chemical properties. They can be classified as either main group elements or transition elements. The main group elements have predictable properties based on their position in the periodic table. And the main group elements are also known as group A elements. So these are all the main group elements, and the ones in the middle of the periodic table are known as the transition elements or transition metals. They have less predictable properties, and they are also known as group B elements. So when you look at the periodic table, you'll notice these numbers above the vertical columns. They're labeled 1A, 2A, 3A, all the way to 8A. So these are your group A elements or the main group elements. You'll also notice numbers above the vertical columns within the transition metals, and these are the group B elements. So when you look at the periodic table, you'll notice these vertical columns, the group A and group B vertical columns. These are known as groups, and the horizontal rows are known as periods, and there's a total of 18 groups and 7 periods. So the elements that fall within the same group have similar physical and chemical properties. So for example, when we look at group 8A elements, these are known as the noble gases. And noble gases are unreactive. They're very stable. So we have noble gases such as helium, neon, argon, krypton, and so on and so forth. Group 7 elements are known as the halogens, and halogens are very reactive as well. They are nonmetals. We have fluorine, chlorine, bromine, just to name a few. We also have group 1A elements, which are known as the alkali metals. And the alkali metals are the reactive metals. They react with water violently. In fact, they cause explosion when they have a chemical reaction. We have lithium, sodium, potassium, and etc. Group 2 elements are known as the alkaline earth metals. Now, these metals are also reactive, but not as reactive compared to the group 1 elements. So we have beryllium, magnesium, calcium, and so on and so forth.